Hi everyone. In this video, we're going to look at how we can use the derivatives of logarithms to make some other types of derivatives either simpler, as is the first case, or possible, which is what's going to happen in the second case. So if I look at this first function, y equals x squared plus 5 to the power of 6 over 3x minus 2 to the power of 4, this is something I can derive using previously learned techniques. So we can derive this function using a combination of the quotient rule and chain rules, but it's kind of lengthy and it gets messy. Whereas we can use properties of logarithms which allow us to turn complicated functions into simpler functions to make the derivative easier. So the log rules allow me to turn products into sums, quotients into differences, and powers into multiplication. So that's what's going to come in handy here. Essentially, I'm going to take the natural log of both sides of this equation. So this becomes the natural log of y equals the natural log of x squared plus 5 to the power of 6 over 3x minus 2 to the power of 4. But now because of log laws, I can turn this into 6 ln of x squared plus 5 minus 4 ln of 3x minus 2, which doesn't involve quite as much differentiation. I don't have to deal with quotient rule. The chain rule is a little simpler to deal with here. So now when I derive both sides, the natural log of y derives to 1 over y times y prime. The natural log, so this becomes 6 over x squared plus 5. I still do need to apply chain rule, so times 2x. And then minus 4 over 3x minus 2. And again, still apply the chain rule, so times 3, which is 12x over x squared plus 5 minus 12 over 3x minus 2. This means that y prime, so this is still 1 over y prime. So y prime is equal to y times all of this, but here's where I'm going to substitute y back in, because y was equal to x squared plus 5 to the power of 6 over 3x minus 2 to the power of 4 times 12 over x, or 12x over x squared plus 5 minus 12 over 3x minus 2. So I can see that I just have my original function, so this whole bit right here, that was y. So when I multiplied y on both sides of the equation, and I have the same critical values that I had from that function, it's just now if I needed to find new critical values, I would only have to solve the equation where this second set of square brackets is equal to 0. So that is the new derivative using logarithmic differentiation. In this case, I didn't need logarithmic differentiation, but it made things a little bit simpler in terms of the work in the middle of this problem here. For this second example, though, I need logarithmic differentiation. I can't simply apply the chain rule here because I can't use the power rule. I can't say that y prime equals x times x to the power of x minus 1, because that doesn't really work. The power rule only applies when your exponent is a constant, and my exponent isn't a constant here. I also can't use the fact that the derivative of an exponential function, so b to the power of x, because that only works when my base is a constant, and my base isn't a constant. So if I have both a base and an exponent that are variable, I'm going to use logarithmic differentiation to split it up. So in other words, I turn this into ln of y equals ln of x to the power of x, which is simply x times ln of x. And now I can derive this using the product rule. So the natural log of y derives to 1 over y times y prime. Then deriving x times the natural log of x. So I'm going to start by deriving x, which is just 1, times the natural log of x, plus x times the derivative of the natural log, which is 1 over x. So this means 1 over y times y prime is equal to ln of x plus 1, which means that y prime equals y times ln of x plus 1, but y is x to the power of x, times the ln of x plus 1. So again, when I multiplied the y on the other side, I didn't bother writing the y, I just wrote what it was equal to, which is x to the power of x. And this right here is the final derivative. So logarithmic differentiation was absolutely essential in the case where you have a variable in both the base and the exponent. If you just have a variable in the exponent, you can use an exponential derivative. If you just have a variable in the base and your exponent is constant, you can just use the power rule. But if you have both, you have to use logarithmic differentiation.